Now we will extract another example of mass moment of inertia. So here the pendulum shown in figure 5.4. Okay, so what is this? If I go to this here, so this is a pendulum, this is a rod, and this one is a rectangular section. The perpendicular or that other axis is not known, so we can consider it is a plate. Now what is the problem is saying that 3 kilogram cylinder rod and 5 kilogram thin plate, and determine the location of the center of mass of the pendulum, and then calculate the moment of inertia of mass about an axis perpendicular to the face and passing through G. Where is our G? Yeah, there the G is here. That means it is the combined centroid. This symbol means the centroid. So we have to determine the mass moment of inertia of this section about this axis and passing through this screen or this phase, whatever you saw. Okay, now this is a thin plate and this is a rod. So we have to find the centroid G first. How to find the similar equation we use to find the centroid of an area. For area we use y1 a1 plus y2 a2. That time a means area. This time same thing, it will be mass, y1 mass 1 plus y2 mass 2 plus divided by m1 plus m2. What is y1? It is the centroid of the mass of section 1 if it is a composite section. So here we will divide this, say this is 1, this is 2. What is the mass of this? If you can remember, it is 3 kilogram. The mass of this is 5 kilogram. So yes, so mass of rod 3 kilogram, mass of plate 5 kilogram. What is the centroid of rod from the hook? It is 6 by 2 because it is uniform. So we can assume it is not assume, we can consider that it is at the middle. 6 divided by 2, 3. What is the centroid of this from here? It will be 6 plus half of this, that means 6.25. Let us see the centroid of the plate. 6 plus half of this, 6.25. So whatever we discuss is right. So then after the calculation we found our centroid. Then how to find the mass moment of inertia of the whole section? First, this portion is the mass moment of inertia of the rod only about its own center and perpendicular to this page, and then plus md square. Then this is the mass moment of inertia of the plate about its own centroid passing through this page plus md square. So this is thus the uses of parallel axis theorem. Determine the mass moment of inertia about its centroid, then transfer it to somewhere by adding md square. So this is m1 y bar minus 1 d square, y bar minus y1. It will give us the distance from the centroid of part 1 to the combined centroid. So we use for this kind of equation in statistics for moment of inertia of mass, moment of inertia of area, same thing. Then we did the calculation where we got this formula, and this formula is listed in the table. If I go back to here, say for the this portion is a cylindrical rod. Is rod here? Yes, rod here. It is m L square by 12 about C passing through G. G means this way. So about this axis, it is m L square by 12. So m L square by 12. What about here? It is we found it from the cylinder. Now if you consider cylinder, this dimension is negligible. We are finding moment of inertia about y. That means oh sorry, not this one. This is the plate. So plate for the rectangular section. So rectangular is not here. We used our book, this one. So we are considering this is our plate. This dimension is negligible, thin. So this can be considered a plate. my dimension is m by, sorry, my moment of inertia about z axis 1 by 12 m a square b square. That is that equation. That is that equation here. Then we calculated our mass moment of inertia of this composite section. Now this example might be very important for AP exam. So hopefully you understood how to find mass moment of inertia of different kinds of section. Just go to the figure and pick the right equation and use it appropriately. Make sure that pound is not a force, pound is not a mass, it is a force. If pound is given, you have to convert pound into mass. Okay, I will wrap up here. Then in the next video we will discuss how to use mass moment of inertia for different computation. Thank you.